Hello dear student, I am Dr. Yogita Thakare, Associate Professor, Department of Chemistry, Shri Shivaji Science College, Amravati. Friends, we have discussed a collision theory, transition state theory, and today we are going to discuss a Lindemann theory for the unimolecular rate of reaction. Now, in collision theory, according to the collision theory, when product is formed, when there is a collision in between the reacting species, the rate of reaction is directly proportional to the number of collisions. But when we consider all collisions, then the calculated rate is very, very high as compared to the practical value. To correct that rate, we have to consider the effective number of collision as well as the proper orientation in terms of probability factor and steric factor or steric factor. We have already know that. Now in collision theory, only the kinetic energy, that is the translational energy of the molecule, is considered. We know that the molecule has the 3 degrees of freedom: translational, vibrational, and rotation. Now in transition state theory, when two molecules get collide, there is a formation of the there is the formation of the transition state which having the high energy. And where that high energy comes from? It comes from when one of the vibrational energy or vibrational degree of freedom is converted into the translational degree of freedom. So in transition state theory, vibrational degree of freedom is considered. Now, according to the transition state theory, the rate is directly proportional to the formation or the concentration of the activated complex for the transition state. And we have derived the thermodynamic formulation for the activated complex theory or transition state theory in terms of the Eyring equation. But what is the reason for the unimolecular reaction? What is the mechanism for the unimolecular reaction? The mechanism for the unimolecular reaction is well explained by the Lindemann theory by giving a theory, that is Lindemann theory for unimolecular reaction. Because when we consider the collision, at least we required a 2 reactant. Now, when the 2 reactants are there, we can say it is the theory or that rate of that reaction or order of that reaction is the second order, or it is not the first order. So for the reaction, that is for the unimolecular reaction, the Lindemann gives the satisfactory explanation. So let us discuss the Lindemann theory. Now, this theory is given by the Lindemann in 1922 to explain the mechanism for the satisfactory explanation for the unimolecular reaction. Consider the unimolecular reaction twice N2O5 gives 4NO2 plus O2. Now, this reaction is found to be first order, but it's very difficult to account the order of reaction using the activated complex theory or the collision theory. Now, for a reaction to occur, molecule must collide according to the collision theory. Okay, and if we consider the collision in between the 2 reactant molecules, then it follows the second order kinetics and not the first order. In 1922, Lindemann explained and used the satisfactory explanation. What is that explanation? That it explained that there is a time lag in between activation and the reaction of the molecule. That is the activation and the decomposition. And during that time lag, the molecule may get deactivated. To understand this concept, consider a simple reaction. A gives a product B. Okay, now mechanism given by the Lindemann for this particular reaction, this reactant A may collide with the another A or the foreign material, so that the second A transfer its energy to the A, so that A star is formed. Now A star is not the activated complex, it is the energized species. So this step is called as activation. And that A star may have chance, or this first state, that is A plus A gives A star plus A, may reverse to form, that is A star plus A gives A plus E. That is called as the deactivation step 2. This is at higher pressure. Now, and again, it may have chance, that is A star may have chance to form a product. In that case, let K2 be the rate constant for the decomposition or the formation of product. K minus 1 is the rate constant for the formation of the energized species. Then K minus 1 is for the deactivation or de-energization of the activation space. Now, here A star is not the activated complex. So what it is? It is simply the energized molecule in vibrational energy level. In other words, vibrational energy of A star exists a threshold energy for overall A gives P. In first step, the energized molecule A star is produced by collision with A, okay, another A, or with the another molecule of A or the foraging material in the system or in the reaction mixture. Now this produces when kinetic energy of second molecule is transferred into the vibrational energy of the first. That is, this transfer its kinetic energy into the vibrational energy of the first, and A star is formed. Now once the A star is formed, okay, once the A star is formed, after production of A star, it can either be de-energized back to A by collision. In this case, that vibrational energy again transferred to the kinetic energy to the A or the foraging material, or that A star can be decomposed or isomerized to form the product P. That is the step 3. So when step 1 is formed, then A star energized molecule may have chance to deactivate or formation of the product, that is decomposition. Now, according to the Lindemann theory, there is a time lag. There exists a time lag in between the first step, that is the energization, and the third step, that is the decomposition of the product. And during this time lag, A star may de-energize back to A. That is, in between the activation and decomposition, the deactivation may occur. Okay, now the rate for the above reaction, we know that the rate is nothing but the rate law equation already we discussed. Rate is equals to minus decrease in concentration of the reactant per unit time is directly proportional to the, according to the law of mass action, is directly proportional to the product of reactant raised to power their number of moles. Now here, the rate of formation of product is dependent upon the concentration of the A star. So in this case, rate is equals to minus decrease in concentration of the reactant A per unit time is equals to K2. K2 is the rate constant for the reaction into concentration of A. Let this is equation number 1. But now here A star is the energized species. We cannot have the value of it because it is formed meanwhile or in the reaction mixture. Okay, it is not the starting material or the final material. So how we can find out the concentration of the A star to find out the rate? Okay, we cannot have the value of concentration of A. So in this case, when the energized species is there, okay, which is that is the unstable species which is formed or which is the intermediate in between the reaction, then we use the steady state approximation for that shortly lived species or to have the concentration of that shortly lived species. Now, how we can find out the concentration of A star? Just we have to take the rate of its formation is equals to the rate of its decomposition. So we have to take all the term where it formed, okay, on one side and where it decomposed on another side. If we can look towards this or step 1, step 2 and step 3, then here A star is formed. So this is step for the formation. Here A star is, okay, A star is the reactant, okay, it may be deactivated and here it is decomposed. Okay, so here there is a formation of the A star, so K1 into concentration of A into concentration of E. So by using steady state approximation to find out the concentration of the shortly lived species, what we get, rate of formation of A star is equal to its rate of decomposition. So in the first step it is formed, so K1 into concentration of A into concentration of E. But in the step 2, and step 3 it get decomposed. That is K minus 1 into concentration of A star into concentration of A plus K2 into concentration of A star. So here the rate of decomposition of A star we will get how? K minus 1 concentration of A star into concentration of A plus K2 into concentration of A star. Now what we have to find out? We have to find out the concentration of A. Okay, what we have to find out? We have to find out the concentration of A. So take concentration of A star common. So this is A star common. So what is remaining? K minus 1 into concentration of A plus K2. Okay, is equals to K1 A into A, that is A square. K1 concentration of A square. Therefore, from equation 2, what is the concentration of A star? Concentration of A star is equals to K1 concentration of A square divided by K minus 1 into concentration of A plus K2. Okay, so this is the value of concentration of A, equation number 3. Now, substitute this value of concentration of A star in equation 1. So what we get? R is equals to minus dA by dt is equals to K2 is equals to K2 into K1 into concentration of A square, K1 into concentration of A square divided by K minus 1 into concentration of A plus K2. So this is the rate law equation for the Lindemann theory. But if we look towards this equation number 4, then this is not in a definite order. Because A is here, A square is here, A is here, it is not in a definite order. Okay, now to have this equation number 4 in the definite order, we have to apply the two conditions. We have to apply the two conditions at high pressure and at low pressure. Now, at high pressure. Now, when the pressure is very, very high. Now, when the pressure is very, very high, at a high pressure, the rate of deactivation is predominant. The rate of deactivation is predominant. I have already write here at high pressure, the rate of deactivation is predominant. That is K minus 1 into concentration of A star into concentration of A is very, very high. That is K minus 1 into concentration of A is very, very greater than the rate of decomposition K2. So here K minus 1 into concentration of A is very, very high than the K2. So it is very, very high. So K2 is very, very small. So K2 can be neglected from this equation number 4. So what we get? R is equals to at high pressure. K1, K2 as it is, concentration of A square as it is, K2 is neglected, K minus 1 into concentration of A. Now friends, you can see here, this concentration of A and this square, okay, 1A from this square get cancelled. So what is remain? R is equals to K1, K2 into concentration of A divided by K minus 1. So what we get? R is equals to K1, K2, K minus 1 into concentration of A. K1 is constant, K2 is constant, K minus 1 is also constant. Therefore, this is constant. R is directly proportional to the concentration of A. So, what is the order of reaction? It is 1. So, what is asked in the MCQs? जे विद्यापीठाचे मल्टिपल चॉइस क्वेश्चन्स आहेत त्यात तुम्हाला काय विचारतील किंवा नेट सेटच्या एक्झामिनेशन मध्ये तुम्हाला काय विचारतील? At high pressure, unimolecular reaction is found to be unimolecular, bimolecular, first order, it follows the first order kinetics, second order kinetics, third order kinetics, zero order kinetics. So what is your answer? Okay, at high pressure, the unimolecular reaction follows the first order kinetics. Now we will take a second condition, that is at low pressure. I have already write here, that is at low pressure, the rate of decomposition is more, that is K2 is very, very high. Okay, so at low pressure, okay, at low pressure, the rate of decomposition is predominant, that is K2 is very, very greater than K minus 1 into concentration of A. This is our equation. So K2 is very, very greater than K minus 1 into concentration of A. So this can be neglected. K minus 1 into concentration of A can be neglected from equation 4. So what we write from equation 4? R is equals to K1, K2, concentration of A square as it is divided by the K2. Now we know that K1 activation rate constant, K2 this is we can say the decomposition rate constant and the This is K2. That K2 get cancelled. Okay. Rate constant for the decomposition cancel. Then R is equals to what we get K1 into concentration of A square. That is R is directly proportional to the raised to power of A. Okay. Raised to power 2. Okay. So at low pressure, it follows the second order kinetics. So it is asked in the in the form of multiple choice questions in your university examination. That at low pressure, okay, the unimolecular reactions found to be first order, second order, or whatever may be the options, your answer is the second order. Now, the experimental rate constant, as this is the unimolecular reaction, this suppose A is converted into the P, experimentally, what should be the rate of reaction? R is directly proportional to the concentration of A. If we consider A is the bride. This is the mechanism given by the Lindemann. But if we consider the unimolecular reaction, the rate is directly proportional to the concentration of A. So for the unimolecular reaction, what we can write? R is directly proportional to the concentration of A. As K1 we have taken, K2 we have already taken, K minus 1 we have already taken. So here I will take K uni, that is rate constant for the unimolecular reaction. So for this unimolecular reaction, what should I write? R is equals to K uni concentration of A, where K uni is the rate constant for the unimolecular reaction. Now, R is equals to K uni into concentration of A. This is the general rate equation for the unimolecular reactions. And the equation 4, we have derived from the Lindemann mechanism. R is equals to K1, K2 concentration of A square divided by K minus 1 into concentration of A plus K2. So both are the rate for the unimolecular reaction. We will equate them. So we have equate this equation. Okay. So we will get the equation, this equation from equation 4 and this equation 7. That is K uni into concentration of A is equals to K1, K2 concentration of A square divided by K minus 1 into concentration of A plus K2. What we do now? We divide from both the side to both the side by concentration of A. Then here K uni concentration of A divided by concentration of A only K uni. Now here if we divide by concentration of A, it is only A. So what I get K uni is equals to K1 K2 concentration of A divided by K minus 1 into concentration of A plus K2, or K uni is equals to, if I again here divide by the concentration of A, okay, K1, K2 divided by A here, again here divide by A here. So AA get cancelled here and here also AA get cancelled. So what I get? K uni is equals to K1, K2 divided by A get cancelled, K minus 1 plus K2 divided by concentration of A. It is given by the Ki or K Roman 1. K Roman 1 we can say, K Roman 1, that is rate for the unimolecular, rate constant for the unimolecular reaction K uni or K Roman I. K Roman 1. So the equation 8 represents the rate of unimolecular reaction according to the Lindemann theory. Okay. Now again I will simplify this equation. Already we know this. K uni concentration of A is equals to K1 K2 A square divided by K minus 1 concentration of A plus K2. Okay, I divide the equation by concentration of A, then I get this equation. Again we divide the concentration of A to this side only, so I get this equation. Okay, before that we will just take a reciprocal. So up to this we have already derived this equation. Okay, so take a reciprocal, because here we have to plot the graph, and to plot a graph we have to take this equation in the form of y is equals to mx plus c. So we get this equation. Okay, this is similar as this equation we already discussed. So K uni is equals to K1 K2 concentration of A divided by K minus 1 into concentration of A plus K2. Now just take a reciprocal. What I get, 1 upon K uni is equals to K minus 1A plus K2 divided by K1 K2A. K1 K2A. So I will get this equation. Okay, or again this is plus sign is here. Okay, so the denominator is same. Again after simplification what I get, 1 upon K uni is equals to K minus 1 concentration of A divided by K1 K2 concentration of A plus K2 divided by K1 K2 concentration of A. Okay, here K2 K2 get cancelled. Okay, K2 K2 get cancelled. Here concentration of A get cancelled. So again, after simplification, what we get 1 upon K uni is equals to K minus 1 divided by K1 K2 plus 1 upon K1 into concentration of A. Okay, again I rearrange this equation in the form of this 1 upon K uni is equals to, I have write this at first time, that is 1 upon K1 into concentration of A plus K minus 1, K1 and K2. Again, I rearrange this equation in the form of y is equal to mx plus c, that is 1 upon K uni is equals to 1 upon K1 into 1 upon A plus K1, K minus 1, K1, K2 as it is. Now this is in the form of y is equal to mx plus c. That is when we plot a graph in between 1 upon K uni and 1 upon A minus concentration of A. Okay, when we plot a graph in between 1 upon K uni and 1 upon concentration of A, then we will get a straight line having slope 1 upon K1 and intercept K minus 1 divided by K1 K2. So here is the graph 1 upon K uni, or we write K uni as a K Roman 1. Okay, so 1 upon should be there. Huh? Here 1 to crop anyway. So 1 upon K Roman 1 or 1 upon K uni. Okay, versus 1 upon A. So we get a straight line having slope 1 upon K1 and intercept K minus 1 divided by K1 into K2. This is our theoretical, we can say the straight line. Okay, making and intercept this to the y-axis. Okay, but actually experimentally what is observed, experimentally there is a deviation and we will get this line. There is a deviation. Okay, and we will get this line. Okay, now here there are some criticism for the Lindemann theory for unimolecular reaction. Drawbacks for the Lindemann theory of the unimolecular reaction. Now, in this unimolecular reaction, the order changes from first order to second order. We know that when we take the two conditions, that is from high pressure, it is first order, high pressure to low pressure, it is second order. Okay, at high pressure, it is first order, at low pressure, it is second order. So in this unimolecular reaction, the order changes from first order to second order when the pressure changes from high pressure to low pressure. This fact is supported by the radiation theory. It gives satisfactory qualitative interpretation for the unimolecular reaction, but quantitatively, it is not completely satisfactory. Why? Because there are the two main difficulties in the Lindemann theory. Now, first one is the first order rate constant should far away at a much higher pressure than was actually observed. Therefore, error must be in the estimation of the K1, and this difficulty is overcome by the Hinsel-Wood theory. Okay, हे समजलंय का तुम्हाला? बघा, this is the unimolecular reaction, so it should follow the first order kinetics. It should follow the first order kinetics. Means we have to evaluate the value of K1. We have to evaluate the value of, we have to calculate the value of K1. But what is observed? The first order rate constant should far much away at higher pressure, because at high pressure it follows the first order kinetics. But whatever the values are there, the first order rate constant should far away at much higher pressure than was actually observed. There is an error in between the practical value of K1 and calculated value of K1 at high pressure according to the Lindemann theory. And therefore the error must be in the estimation of the K1, and this difficulty was overcome by the Hinsel-Wood theory. Okay, आता बघा Hinsel-Wood theory ने ही difficulty overcome केली. त्यांनी K1 काढला आहे. जो काही त्यांनी व्हॅल्यू काढली आहे K1 ची ती मॅच होते. का बरं मॅच होते? कारण हिंसेलवूड थिअरी मध्ये आपण एकच व्हायब्रेशनल डिग्री ऑफ फ्रीडम कन्सिडर केली आहे अकॉर्डिंग टू द ट्रान्झिशन स्टेट थिअरी. मग आता आपल्याला काय करायचं आहे, टोटल व्हायब्रेशनल डिग्री ऑफ फ्रीडम कन्सिडर करायचं आहे. कारण एकच व्हायब्रेशनल डिग्री ऑफ फ्रीडम जर कन्सिडर केली तर तेवढेच एनर्जी मिळेल, तेवढेच मॉलिक्युल्स ऍक्टिव्हेट होईल, तेवढाच आपल्याला प्रॉडक्ट मिळेल. बट इफ वी कन्सिडर ऑल व्हायब्रेशनल डिग्रीज ऑफ फ्रीडम, more and more molecule get energized and converted into the product. So the first drawback is we can say it is overcome by the Hinsel-Wood theory. Hinsel-Wood theory मध्ये आपण काय काढणार आहोत, K1 considering all vibrational degree of freedom. या नंतरच्या लेक्चर मध्ये मी तेच घेणार आहे. Okay. And second drawbacks of the Lindemann theory is when we plot a graph 1 upon K uni versus 1 upon A, we should give a straight line. This should get, okay, theoretically, okay, we should get a straight line. However, deviation from the linearity was observed, but experimentally we will get this type of the curve, and this difficulty was overcome by RRKM theory. This difficulty was overcome by the RRKM theory. So to remove the first difficulty, we have to study the Hinsel-Wood theory, and to overcome the second difficulty, we have to study the RRKM theory. So thank you for your kind attention. We will discuss the Hinsel-Wood theory in the next lecture.